In this video, we'll talk about how to study integer compositions using ordinary generating functions. To start, let's look at a minor variation on our sequence construction. So here, this will be sequences where we have length greater than or equal to 1. So our usual sequence construction would be slightly different because we throw in a sequence of length 0. But in this case, we're looking at sequences of length greater than or equal to 1. So we would just have z plus z cross z, and then 3 copies of z, and so on. And in this case, again, this curly z is an atomic class. And you can think of lots of other variations on this notation. In fact, sequence just sub k, this should make it more curly, is just the k-fold product. And you could do this with other things in place of z. And this turns out to be isomorphic to just the natural numbers because I have one element of size 1, I have 0 elements of size 0, I should say, and then I have one element of size 2, one element of size 3, and so on. So the ordinary generating function of the sequences of size 1 or more will give me z over 1 minus z, because this is z plus z squared plus z cubed, and so on. Okay, but these are not integer compositions. These are the natural numbers. We get compositions by taking sequences of natural numbers with the appropriate notion of size. So integer compositions will be the combinatorial class sequence of I. And you can think of this as, since I is isomorphic to the natural numbers, or the positive integers, these are sequences of positive integers. But we also have a notion of size. So the sequences of positive integers of size k will be lists of integers. So L greater than or equal to 0, many of them, x1 through xl in the natural numbers, such that x1 plus x2 all the way up to xl adds up to k. So this is another way of saying lists of positive integers that add up to k. So the elements of size k will exactly be this set, but the whole class will be all of these possible sequences of positive integers with this notion of size. And we can easily just write down what the generating function is now because it's built from the sequence construction. It's a little more complicated because we're doing a sequence of a sequence, but we can still do it. So the generating function will be 1 over 1 minus the ordinary generating function of I, which was z over 1 minus z. And then we can actually simplify this into this form. And if you play around with it a little bit, you can write it here, and you can get out an actual formula for the coefficients. So it'll start out as 1, 1, and then it goes to 2, 2 squared, 2 cubed, z to the 4th. And so it turns out that the formula is Cn equals 2 to the n minus 1 for n greater than or equal to 1, and then C0 equals 1, because we have this kind of empty, we have one empty sequence, so it's one thing of size 0. So I guess that's just saying that if you add up no positive integers, you'll get 0. So sometimes the trivial cases have to be handled carefully, but in any case, we get this immediate formula for the number of integer compositions, which you can come up with combinatorial explanations for why this should be the right formula, but in this case, we don't have to. So we can talk later about how you would do this from a sort of bijection perspective, but we don't have to. Okay, so there are lots of variations on this. We can look at restricted summands. So the first example of this would be to look at compositions using only 1 and 2. So now we're viewing 1 as an element of size 1 and 2 as an element of size 2. And if I take sequences in 1 and 2, let's see, so I'll take, I'll have a list of 1s and 2s, and I'll have a notion of size. So the notion of size would be to just add up all these numbers. In this toy example, I'll get, let's see, 4, 5, 6, 7, 8. And so this is a way of writing 8 as a sum of an ordered sum of 1s and 2s only. And we've actually already seen this in the example in the last video using the sort of lists of dots and bars. The ordinary generating function of this class, which again had one element of size 1, so we get a z, and one element of size 2, so you get a z squared, gives us sequence of z plus z squared, so I'll get 1 over 1 minus z squared. And so this is immediately giving me the generating function for this counting problem of the number of ways to write an integer as an ordered sum of 1s and 2s. Now, it's worth pointing out in this simple case that you can use partial fractions to solve this exactly. And so I already mentioned in the last video that this gives you the sequence of Fibonacci numbers, but let's look at it here. So this is again the explanation of why you have the same recurrence as the Fibonacci numbers. So let's write out the ordinary generating function notation. And we have the same recurrence that the Fibonacci numbers have, since a composition, so if I have a number written as a sum of 1s and 2s, it either ends in a 1 or a 2. So every one of these compositions can be associated to either a composition of one lower number or two lower numbers. So that's just to illustrate the connection of the Fibonacci numbers. And this is a recursive way of trying to understand the sequence, which is not going to be our focus in this course, but it's worth pointing it out here because you get this famous sequence. Okay, but you can use partial fractions that you learn in calculus to actually find a formula for the Fibonacci sequence. And if you've not seen this before, I think this is pretty amazing. But okay, so to do partial fractions, I have, I look for the zeros of the denominator, and I just use the quadratic formula here, and so I get that z is 1 plus or minus root 5 all over 2. And so this number is called the golden ratio. It's 1 plus square root of 5 over 2. And it turns out that z is either this or 1 over that. It turns out the roots are reciprocals of each other. That's not obvious, but you can multiply them and see it. So the two roots are phi and 1 over phi. And so we can factor this into a constant over 1 minus z over phi plus a constant over 1 minus phi z. And I've tried to write this in a convenient way. You might be more used to writing out something along the lines of this. But I like to kind of keep the 1 here because then I can do a geometric series with what's left. So I'll do it the way I have it here. Okay, and then you just have to do some solving, which I don't want to belabor this point, but you would multiply this out and set it equal to 1, as we have on the left side. And so you get a plus b is 1. You get some more complicated thing for the coefficient of z being 0. But eventually you get what the coefficients are. So I encourage you to go through this on your own. It's maybe boring to watch it, but I think you get a is this and b is this. And so the partial fraction decomposition of this function turns out to be here. And then each of these terms can be written out using a geometric series. So this term here, I'll have a phi in front, but then the rest will be this geometric series. And similar for this piece, you'll get a phi to the j plus 1, because this extra phi minus phi to the negative j plus 1. We also had this 1 over root 5 out front. And this will exactly give us these Fibonacci numbers, or these number of compositions of n using just 1 and 2 will have this formula. And so we're not going to be obsessed with finding these exact formulas always, but we do want to point out that phi is greater than 1, so 1 over phi is less than 1. So this term here is decaying exponentially, and so really this sequence will grow like phi to the n. And that's kind of something that we'll be able to pull out pretty easily later on. Now let's look at a variation of this. So you can go even further and look at compositions using 1 through r. And so this will be a way of encoding the number of ways to write a given integer n as a sum of just the numbers 1 through r. And so this will be a sequence construction of the natural numbers 1 through r, where again we have 1 has size 1, 2 has size 2, all the way to r has size r. And the associated generating function will be just the sequence construction applied to the generating function of the inside, which again will just be z plus z squared all the way to z to the r, but we can simplify this, or at least rewrite it. I can factor out a z, and the rest you can use these sort of partial geometric sum formulas. So I have the sum 1 to z to the r minus 1, and this is equal to 1 minus z to the r over 1 minus z. So I can just put that in here, and you can multiply the top and bottom by 1 minus z now, and if you do the algebra, you'll get this. And I don't want to go too much further than this, so if you look, the book has further explanations. You can use this to find a terrible looking formula for the coefficients of the power series and in some sense solve the counting problem. And I went through it here in my notes, and so I'll post these, but I don't think I should go through it in the video. You can get a formula for the coefficients that's this kind of double binomial sum, but it has changing signs, and how fast does it grow? Who knows? It's hard to tell from a formula like this. But it turns out to be smarter to do something, which is to look at the smallest root of the denominator, and that actually will dictate the growth of the sequence. And so we'll see later that if you find the smallest root of the denominator, we'll see later that this counting sequence of compositions using restricted summands 1 through r, it'll grow like this root to the minus n times a constant. Okay, and I don't know if the video has already gotten a little long, but you can also do something like look at compositions with a fixed number of parts instead of restricting summands. So the integer compositions made of k summands would be ways of writing integers as a sum of k positive integers, exactly k. So now we're restricting the number of parts, not what we use in the sums. And this ends up just being a k-fold Cartesian product, and so this isn't too hard to analyze. The generating function ends up just being this generating function for the positive integers raised to the k power, and you can compute exactly what the coefficients are in this case. And you can look at how they grow, and it turns out that they grow like n to the k minus 1 over k minus 1 factorial. Okay, but this covers some of the basic examples of compositions, and these are all just built from basic sequence, product, disjoint union, and our building blocks from the previous video.